Hey everyone, my name is Jamie from UC Berkeley's PEACE Tutoring, and I'll be taking you through a quick review of linear regression. To start, what even is regression analysis? Regression is a form of statistical modeling where you try to find a relationship between a predictor variable and a response variable. It means that you're trying to fit an equation to a set of data that most accurately predicts a response based on a set of predictors. Linear regression is the simplest form of regression. It is just fitting a straight line to your data set that most accurately represents it. And we can model our data with a straight line, so we have our good old-fashioned equation y equals mx plus b. Y is the dependent variable, or the response variable, which is dependent on a scalar of the independent variable, the variable used to predict the response. Alright, let's look at some data. I have a data set of students at Berkeley, which I totally made up, and how many years they have been in Berkeley and how many years they have been vegan, and then I decide to plot the data with the number of years in Berkeley on the x-axis and the number of years vegan on the y-axis. And then I would see from a data set that it looks like there is a trend and I can fit a line through it. That means I can predict how many years a student has been vegan based on how many years they've been in Berkeley. And then we graph a line that best fits the data and that will most accurately predict our response variable based on our predictor. Alright, as an overview, regression is used for three primary purposes. One, it's used as a casual analysis to look at correlation of some data. It can be used to forecast values or predict a y value based on an x value. And it can be used to predict trends in data. But I just want to clarify that regression and correlation are not the same. Correlation measures how related variables are. It measures the strength of their relationship. And it's important to remember that correlation does not imply causation. That will come up forever and ever, so it's important that you get that down now. It's also important to distinguish that being in Berkeley does not cause one to become vegan. It would be totally wrong to say that. But regression is a model to predict the response y based on a set of predictors, or in this case, just one predictor, our x-axis. And it measures how changing one variable, x, changes the other variable, y, but not vice versa. Alright, so let's go through a quick warm-up to check your initial understanding or what you already know about regression. True or false? Go ahead and pause the video if you can reason out an answer for each one. Number 1. The residual is the difference between the observed value of the dependent variable and the predicted value of the dependent variable. True or false? That is true. The residual is just the error, the difference between the observed value and the expected value. Number 2, if r, the correlation coefficient, is equal to 1, then we can conclude that there is a perfect relationship between x and y. That is true. There is a perfect negative relationship between x and y. This is a question of correlation, not regression. This is testing to see if you know what correlation is. Number 3. In a simple linear regression model, the coefficient of determination not only indicates the strength of the relationship between the independent and dependent variable, but it also shows whether the relationship is positive or negative. That is false. Linear regression does not deal with the strength of the relationship. This is totally describing correlation, not regression. And number 4. The least squares simple linear regression line minimizes the sum of vertical deviations between the linear regression line and the data points. This is false. Least squares minimizes the sum of squared vertical deviations. That's a really tricky one. You really have to know what's going on. Alright, so remember that regression is all about finding the best fit line for the dataset. We're trying to find the most accurate relationship of y described by x. So if there's an association between the predictor and the response variables, we want to know if we can model the data or predict years vegan based on years in Berkeley. So the first thing that you have to figure out about your data is if it's football shaped. If it doesn't look like a football where you can't fit a line through it, then the deal is off. You cannot do linear regression. But more interestingly, the axes are in increments of standard deviations of each variable. Meaning on the x-axis, one tick mark to the right of the center is one standard deviation up from that point, and one tick mark to the left of the center is one standard deviation below that point. And same goes for the y-axis. The increments are in units of standard deviation. So you can do a quick visual check with yourself. 68% of the data of the football shape should lie between -1 and 1 standard deviation. And same goes for the y-axis variable. Remember, the regression line will not fit the data perfectly. You will have some sort of vertical deviation from the line, from all of your data points to the regression line, and that is called error. That's how far off each point is from the regression line. But to get a big picture number of the overall error around a regression line, we use the root mean squared error. This quantifies how off all of your data is from the regression line, just like how standard deviation is used to measure variability around a mean. Mean squared error is used to measure spread around your regression line. RMS error is essentially the standard deviation around your regression line. So the area between one RMS error above and below the line accounts for 68% of the data. An RMS error approximates the spread around the data more accurately than using either the standard deviation of the x-axis or the y-axis alone. Alright, one common question you will see is, of the data points that have a certain x value, what does the distribution of y look like? Or can you give any information about how likely y is to be between a certain point given a value of x? Let's go through an example of that. Of those who scored 165 on the LSAT, about what percentage had first-year scores above 75? For this question, you need to look only at the data points that had an LSAT score of 165 and then look at the spread of y data on that y-axis at that point. Remember, the y-axis, first-year scores, has its own distribution, so this set of data behaves just like its own mini distribution, with its own average and its own standard deviation. So now you need to know the new average of that sub-data set and its own standard deviation. Right, so how do we figure that out? We know that the average LSAT score is 162 and the standard deviation is 6. And the average first-year scores is 68 and its standard deviation is 10. And you are given a correlation value of 0.6. The first thing that you need to do is find the values of the equation of your linear regression line. So find m and b. M is your slope and b is your y-intercept. Right, the slope m is given by the correlation value times the ratio of standard deviations of the y-axis to the x-axis. And since we already know a point on the line, the average, we can plug both of those numbers in to find the intercept. B equals -94. Alright, so now that you know the equation of the regression line, you can find the new average y value of people with LSAT scores 165, plug in 165 as x, -94 as b, and m as 1, and your new y value is 71. So from the regression line, on the regression line, people with LSAT scores of 165 will have an average score of 71. But there's, of course, a spread of values that comes with that last statement. So what is the standard deviation of the new subset? Because it has its own average, 71, and its own distribution. So we need to figure out what's the new standard deviation of that subset. That's actually the RMS error. Remember that RMS error was just the square root of the sum of squared vertical deviations. So we calculate RMS error from the formula, standard deviation of the y-axis multiplied by the square root of 1 minus the correlation squared. And then we get our RMS error value of 8. Now back to the question, what percent had first-year scores above 75 given an LSAT score of 165, plug in 165 as x, -94 as b, and m as 1, and your new y value is 71. So from the regression line, on the regression line, people with LSAT scores of 165 will have an average score of 71. But there's, of course, a spread of values that comes with that last statement. Well, since we know the new average and the new standard deviation, we can just use that to calculate our z-score. Well, since this is just a standard distribution, and we know the new average and the new standard deviation, we can just calculate our z-value. Z is our subject score, 75, minus the average, 71, divided by the standard deviation of our new distribution, which is 8, to get a z-value of 0.5. Now we look this up on our good old-fashioned z-table and find the area to the left of z is 0.6915. But this question is asking about the area above 75. So 1 minus 0.6915 equals 0.3085 or 30.85%. Alright, equipped with this knowledge of how to do linear regression, I encourage you to try a problem on your own to really check your understanding. Here we have subjects with their age and glucose levels measured in units of milligrams per deciliter, and I want you to try to find a linear fit of glucose level predicted by age. Once you have that, find the predicted glucose level for someone aged 60, and then try finding what percent of subjects have glucose levels over 85 for someone aged 25. Now, this is not a lot of data, obviously. When doing regression analyses or any analysis at all, the more data you have, the better, and the more accurate your prediction is going to be. But here you have to calculate everything by hand, starting from averages, standard deviation, and the correlation coefficient, and then you have to answer the problem. So we only give you a few data points here. All right, thank you for listening. Thank you to Gaston Sanchez for the awesome slides. You can check out his website here. I got the previous question from Statistics How To, or you can check out the problem on this link. And again, thank you to PEACE Tutoring. All right, guys, good luck.